Okay, so I drew this cartoon because I think it's really important to, before we dive into what bidirectional transformations are, to really think about what we're doing here in the first place. Why is software engineering difficult? Because I think this is all fundamentally the same reason is why software engineering is difficult, is why we want model-driven engineering, and is why should we be interested in bidirectional transformations. Okay, so the same justification justifies all of these things, and it is because there is too much information that has to be understood when you try to build a complicated software system. The details really matter. There are many details where if you get them wrong, the eventual software system doesn't do what you want it to do. And there are too many of them for any one human to be able to hold them all in mind at once. Okay, and that is the fundamental problem that all of our approaches to how to do software engineering better are trying to tackle. And bidirectional transformations is going to be no exception. Now I have to move in the right place. Yeah. So you can see all of these approaches to software engineering as being fundamentally about how do we control this overwhelming amount of information that goes into building a large software system. So all the different kinds of abstraction that we do are to do with this. So we develop high-level programming languages. We architect our systems so that there are components, each having interfaces. We think about how to verify things, so about how to state a test or that a system ought to pass, or a property that it ought to satisfy, and then we think separately about how to check that the system does actually pass that test or how it satisfies that property. And in all of these cases, what we're doing is we're saying, I, as a human with finite memory and finite processing power, want to be able to make progress on changing this software system or fixing it, changing it so that it is how it should be. But I want to be able to do that without having to simultaneously understand everything about it. Okay, so a high-level language abstracts away from, what the computer is actually going to do at the register level, and the interface abstracts away from how a component is implemented and just tells you something about what it's going to do. And our verification techniques are all about saying, I don't care how the system passes this test, I just want to make sure that it does in fact behave the way this test says it should behave, and so on and so forth. And we have this phrase, separation of concerns. This goes back to Dijkstra, doesn't it? Which is all about this. It's about saying, I want to be able to think about one aspect of my system's behavior without being constantly distracted by information that isn't relevant to that concern, to that aspect of my system's behavior. Okay, and that's why we have models. Okay, so the point about a model is it's a representation of a concern. It's a way of saying, here is a documentation of all the information that is relevant to making decisions about something about the system, but not everything. So it deliberately excludes a lot of information that isn't unimportant, but it's unimportant for one particular purpose that the model is trying to support at the moment. Okay. And you can even, incidentally, think about things like bounded small releases and approaches like you ain't going to need it as being the same kind of thing, but this time not in sort of space across the design of a system at one moment, but across time. So again, you're saying, I'm not going to think about, the fact that the customer is going to want such and such an advanced feature, even though I already know it. For now, I'm only going to think about the functionality that I've decided to put in my first small release, okay, in order to focus my limited attention. And when I talk to students about this, I like to talk about what would happen if we one day met, the little green aliens from planet Zog, and we investigated how they do software development. Because the issues about whether we could join their software development teams or they could join our software development teams would be very little to do with computer science, properly speaking, and they would be all about the cognitive capacity of those little green aliens, whether they had the same kind of amount of working memory and the same kind of processing power as us, because that's what determines how we organize our software development, much more than the capabilities of the machine, the computer. So that's kind of setting the scene. So the whole of model-driven engineering is about saying we want to separate concerns. We want to have models which record some of the information that's important, but not others. So this is why we have models in the first place. I'm going to skip that because that's not relevant to today's purposes. So once you've split the information in your software development system into a bunch of chunks, that already actually helps a lot, because it enables you to sort of have a clear desk and think about one aspect, the aspect which is represented by a particular model or a particular file or whatever it might be. But there's a sense still in which difficulty is conserved, because at some point you still have to integrate the chunks because they still have to all work together. So you have to end up with a software system which is correctly modeled by all of your models, regardless of how they've changed over the course of the software development. If you've got a bunch of different files, program files, they've all got to compile correctly together, and they've all got to work together, and so on. So we've got a bunch of techniques today which are quite good at supporting individuals in temporarily focusing on one concern, but we don't yet have very much support in helping people to do the work of reintegrating those concerns, of bringing them back together, of making sure that decisions that were taken in the context of the information only about one concern don't break things in another concern. So all these decisions have got to work together in the end to end up with one coherent software system which will actually do what we want. Okay, so that's what this picture is showing. We're saying, so now let's think explicitly in terms of model-driven engineering and say, suppose that we've got an engineering setup in which we've got a bunch of different models. So I've got blue ones, red ones, and purple ones here. And they are all being worked on by different experts who are experts in these particular concerns. So I think what I was trying to suggest in this picture is that we've got maybe some system architects in red who are dealing with the overall structure of the system, and perhaps we've got some interaction designers in blue who are looking at how users will experience the system as they go from one screen to another. And in purple down here in the left, we've got some people who are working with Greek symbols, and so they are probably doing something that's maybe safety related or something like that. And in the end, all of these models have to be integrated together and have to produce an actual running system that people can kind of sit at screens and use. Okay. And so our focus today, when we're talking about integrating these models, is about this process of bringing them all together and keeping them all together such that they work together in a sensible way and change together in a sensible way. And that's what bidirectional transformations are all about. The bidirectional transformations are the coloured wires. So they represent the process, and it might be a manual process or an automatic process or a partly automated process, of reintegrating the chunks of knowledge that are represented by the various models. Okay. And we're much less good at designing and maintaining and thinking about those coloured wires, those bidirectional transformations, than we are at this stage in our history of understanding how to do software development, at developing languages in which models can be expressed and models themselves. We're quite good at that. We're much less good at the reintegration. So we're good at this point at separation of concerns, and we're much less good at reintegration of concerns. Now, how are we doing so far? We've got no questions in the chat so far. Okay, so that's what bidirectional transformations are for. Bidirectional transformations are for integrating concerns. Now, I have to confess that after a while, after you've been thinking about things in terms of bidirectional transformations for a while, everything starts looking like bidirectional transformations. You start looking at everything through your books glasses. And I almost kind of want to make that a feature, or perhaps even a philosophical point. There's a case to be made to say that actually the essence of computation is not functions producing outputs from inputs at all. It is the identification of consistency and of how to restore consistency. I think you can argue that that's really what computational thinking ought to be about, consistency and its restoration. I don't want to push that too far. Let's come right back to earth at the moment and say, I've been sort of talking about models and model-driven engineering. What are we going to mean by a model in this context? Well, some of you have heard me say already, everything's a model. Okay, so at the level that I like to think about things, it doesn't really matter very much. Very much the same considerations arise, whether we're thinking about a model as being a graphical representation of some aspect of a system, or a textual representation of some aspect of a system, or whatever it might be. And so I'm going to use today I'm going to use the term model in this very general sense. And quite a lot of today, we're going to think about models as certainly including things like files of Java programs, or files of JUnit test suites, or all this kind of thing. So I don't care whether models are graphical or textual for today. So here are a few examples of things that we might think of as being models. I won't read them out at this point. I think earlier on said the key thing, a model is a representation of a concern. So the point of a model is that it's going to support the work of a particular group of people. We should think of it as being a thing which records all and only the information that somebody or some group of people need to do their work right now. Okay. And so having multiple models in your system is an automatic consequence of wanting to do separation of concerns. So if the models that we've separated our information into were completely independent, orthogonal, okay, and sometimes that's the case, then life is very easy. Whenever you can separate information into independent chunks that have no dependencies on one another, you should certainly do so, because that makes your life a lot easier, realizing that you don't have to do anything. You don't have to do any work to reintegrate those chunks. Reintegration comes for free because there are no consistency constraints between them. That's great. But generally speaking, you're not in that nice situation. You have some dependencies between your different information sources, and they have to be managed somehow. So I'm going to have us think for a little while about a concrete example, which is the case where we've got some Java code. I don't really care how much. You can think of it as being a single class, or you can think of it as being 1,000 classes in a system. And we've got a test suite. And just for concreteness, let's suppose that our test suite is, also recorded in the same kind of textual format. Suppose we've got some Java tests. Okay. Now, we've got different people, let's say. We've got a test team and we've got a development team. Test team working on the tests and the development team working on the Java. And because this is the real world, they're probably both making changes simultaneously. Okay, we're not in a real kind of throw it over the wall situation where one was completely developed and then the other one was developed after that. So some changes so even though we admit that we've got some dependencies between these artifacts, it's not the case that any old JUnit will go with any old Java. There are some changes which can be made on one side independently of the other. Okay, so you can refactor the Java, and if it's a true refactoring and it doesn't affect the functionality at all, then you expect to be able to do that without making any modifications to the JUnit tests. Okay, that's pretty much the definition of a refactoring, that you can do that. Thanks for your question, Stephen. I'll come to that in a moment. Other changes might necessitate a change on the other side. So, for example, if you go into the Java and you change the name of a method, then you're going to have to make at least some change on the JUnit side, because the two things won't even compile together anymore if you don't. Okay. And there may be many different ways to restore consistency. for example, if I've changed a method name on the Java side, I could maybe, depending on what I mean by consistent, I could restore consistency by changing the method name correspondingly in all the relevant tests on the JUnit side, or it might be that I'm going to restore consistency by deleting the relevant tests. So there no longer are any tests that refer to that changed name. And you might have an opinion immediately about which of those ways of restoring consistency is better than the others, and I might agree with you. So some ways of restoring consistency between artifacts are better than others. Now, before I go on, let me read Stephen's question and see if I can either answer it or postpone it. Let's see. So Stephen is writing, are you considering an architecture framework approach where you say the reintegration is neglected? I feel like if an architecture framework is constructed properly, then it will have viewpoints that overlap, thereby both separating concerns and ensuring that the concerns overlap. This means in an ideal case, nothing is ever only considered in a single viewpoint and therefore never isolated from the surrounding system. I'm trying to avoid getting into commitment to particular architecture framework approaches. But what I'm trying to point out is that the fact that at present individual developers have to be aware of and familiar with different viewpoints on their decisions is a bug rather than a feature. Okay, it is better if they don't have to do that. At the moment, they do have to do that because typically speaking, the only way we get to integrate change decisions that are made in different viewpoints correctly is by applying human intelligence to do that. That's why software development is difficult, because even though we support humans in temporarily focusing on one concern, working with currently in one viewpoint, typically the same people will also have to raise their head above the parapet and look at the other viewpoints from time to time. And this is quite difficult. It requires, understanding a whole bunch of things that are related. This is why software developers get paid the big bucks. And yes, we have some good frameworks for, to some extent, supporting that process. But what we don't have yet is enough support for actually saying you never have to understand anything other than the thing that you want to be an expert in. And this becomes really important when we start thinking about future software development, or development in which we would really like, ideally, to be able to take most of the decisions about how a software system should behave out of the hands of the expert software developers and give them directly to the stakeholders. So in an ideal world, what you'd like to deliver is the capability to get software to meet your needs in an organization, even as those needs change. So what you'd like to do, I claim, is to hand, say, to the finance manager in your university, the ability to collect the information that they're going to need and have it correctly recorded in the database and reported via the accounting systems and so on. You'd like them to be able to say, my needs have changed. I now need to collect this extra piece of information, or I don't need to collect that one anymore. I'd like to just change that in my nice usable model here, and I'd like to press a button to have everything else about the software system updated correspondingly, instead of saying I'd like to make a business case for going back to the software developers and asking them to deliver a new version of my software system that will meet my now slightly changed demands. So I'm fantasizing here, but in the ideal world I would like us to be moving towards that. So that's part of the motivation for thinking about better separation of concerns with better supported integration of concerns. It's in order to reduce the level of skill that is required for somebody to be able to do that. Okay. So I hope that answered the question to some extent. So when we think bidirectionally, we fundamentally got two tasks, and it's worth separating them out in our heads. We've got consistency checking, which is about saying, suppose you have two or more models of your system. How do you know whether you're in a good state? So I've said here all is well. What I mean here is something like, are we in a state where we're satisfied that there aren't inherent contradictions between the decisions that have been made and recorded in the different models that we're trying to check consistency between? Okay, I'm being woolly. I'm going to ask you to concretize this in a moment, but there should be, and we should, and if we're doing bidirectional thinking, we should make explicit a notion of whether or not all is well at the moment, whether or not our models are currently consistent. Okay, and so we should be able to answer that question. We should be able to say, okay, looking at all of these models at the moment, are they in a consistent state or are they not? Okay. And a second question, a different question, is how, if they're not consistent at the moment, are we going to restore consistency? Are we going to move from that inconsistent state back to a consistent state of all our models, of all our viewpoints? And so we've got a bunch of choices here. We've got a choice about how much we want to articulate about all is well. So there's some sense in which if you were all-knowing, you had a crystal ball, you could see where development was going to go from now, you'd know a lot about whether or not there are problems. You would say, well, if we continue development from this point without changing anything, are we going to run into problems or not? And you'd say, if we're going to run into a problem, then there's an inconsistency, and if not, not. But when you actually want to record what's going on here or articulate it, or let alone think about automating anything, you've got a choice about how much to articulate, how much are you actually going to insist on, because you can't foresee the future, so you can't actually articulate absolutely everything. We'll come to this in a concrete sense in about 2 minutes. Separately, you've got a choice about how much you're going to automate the restoration of consistency. Okay, and then there's a bunch of other things that we may or may not get to depending on how we choose to use the time. You might want to think about what kind of fixes you want to consider. Do you only want to consider changing one model at a time, or do you want to consider some kind of negotiation process in which both models might get changed? And a thing that will turn out to be quite important is what information we want to maintain and then have access to in order to do all this, for example, to restore consistency. Do we just want to have the current states of all the models? Do we also want to have some information about what links to what? Do we want to have some history about how we got to this state? Do we want to have full information about, where the user clicked in order to make the change that we're now trying to roll out to other models, and so on? So I'm going to use the abbreviation BOOKS for bidirectional transformation, and ABOOKS is going to be an artifact for automating one or both of those two tasks, the tasks of consistency checking and consistency restoration, and we might be only partially automating it, and I'll get you to talk about that in a moment. But I've talked enough for now. So what I now want you to think about and I'm going to ask you to take about sort of 2 minutes in silent contemplation, and then we'll discuss a little bit what consistency might mean concretely between a test suite, for example, a JUnit test suite, and a program, for example, an implementation of a Java class. Okay, if somebody gave you a piece of paper and said, please write down what needs to be checked in order to check that this JUnit and this Java are consistent, what would you write down? Okay, so now I am actually going to shut up literally for 2 minutes, and then I'm going to invite you to unmute and turn your cameras on and talk about it. So I'm going to shut up starting now. Okay, so that's about 2 minutes. What did anybody think? What might you write? What might you choose to write down if I ask you to write down what it means for your test file and the code file to be consistent? We've got Sebastian in the chat. Says the consistency between test suites and code is difficult to maintain, more specifically when they're developed by different people. Automating this partially might force humans to talk to each other. Yes, hold that thought. We'll come back to that in a moment. But what I want you to be telling me at the moment is just what should it mean for them to be consistent? Antonio, you've got your hand up. Why don't you start?
So I guess the basic thing is if the tests refer to existing classes and methods.
If the tests refer to existing classes and methods, so you mean, for example, that any class or method that is called by a test should actually exist.
Yes.
Yeah, that's one thing you might want. Absolutely, yes. Anybody got anything else?
Maybe not consistency, but completeness. So we would want kind of all methods and classes to be exercised by the tests.
Yep, we might. That's another thing we might want. Yep. Stephen. You're muted at the moment, Stephen.
Well, my first thought would be to construct a conceptual model of both environments and ensure that the conceptual model was explicit and that they were both expressing the same conceptual model.
So I think what you're telling me there is that there should be a notion of consistency. Well, that's agreed. Yes, certainly there should. But the question here is at the moment, what notion of consistency do you actually want? How much do you want to insist? There's no right answer here, right? There are different answers depending on the specific needs of your project. So I'm not going to say, yes, you're right. The whole point here is that there are different notions of consistency that might be appropriate in different settings.
Well, I would say I wouldn't be expecting the entire conceptual model to overlap, but I'd expect there to be an intersection between the model, so that the test model would have to know about the concepts that are being tested, but it wouldn't have to know about the fine-grained detail of all of that. And similarly, the code model wouldn't need to know about the test harness. It would just need to know about the interface to the code. But that bit would need to be tight, and you need to be sure they were talking about the same thing.
Yeah, so that's closely related, I think, to what Antonio said, that things that were referred to in the test should actually exist in the code.
Right, okay.
Okay, anybody got anything else? Don't be shy. There are several other possibilities. So anybody got anything more stringent? Is there anything else is there anything more difficult that you might ideally want to ensure between your tests and your code?
I guess that the tests exercise all paths, all branches, so the kind of more difficult types of testing.
That's a possibility. Yes, that's another thing you might want under certain circumstances. You can see, can't you, that it's going to depend a lot what guarantees you want to be offered by finding that your things are indeed correct. Okay, if you want more of a guarantee, you're going to want a tighter notion of consistency, but there's going to be a greater cost. Stephen, your hand is still up. Is it a leftover hand, or do you want to say something else?
Oh, that was a leftover hand, but yeah, I was thinking about something similar to what Dimitri said. Yeah, I think it was where I was thinking about like bounds checking and that kind of thing. Some of your testing's just going to be interested in the logical aspects of it and the behavioral aspects of it, but then some of it, when you want that more detailed testing, you're going to need to know about the implementation side, the platform specific side as well.
Mm-hmm. Okay, so I hope you can see my slide again now. Yes. So here are a few different things that I think you might want to say, and I didn't set up Antonio and Dimitris to say these things, but you very helpfully did say at least the first couple and the last one. Nobody mentioned that the tests ought to pass, and that's quite an interesting one. Perhaps it's because we because I've already introduced the idea of automated consistency restoration, and we know enough about the price of fish to know that we don't normally expect to have automated restoration of a consistency condition, which would require that the tests passed. But wouldn't it be nice if we did? Wouldn't it be nice if all you had to do was to write a test and press a button, and then your code would automatically get updated so that your test passed? Well, again, if you start thinking in that direction, I'm sure you can immediately see how that would go wrong, can't you? Now I can't see you anymore, so I don't know whether you're nodding or not, but I'm getting ahead of myself here. Okay, so we've got different notions of consistency that we could articulate. So we could have a very lax notion where we just say these things are going to be consistent provided that the files compile together without error. Okay, and that's already going to ensure the kinds of conditions that Antonio mentioned at the very beginning, which is to say that any methods which are called should actually exist, because otherwise the compiler that compiles your test file along with your code is going to complain at that point. The next thing we might want is that there are sufficient tests, that there is a test for every public method. We might want to say that the tests are all going to pass, and we might, as I think it was Dimitris said at the end, also maybe want to say that some kind of coverage criterion was met by the test. So these are different notions of consistency, and all of them might be the right notion to have in a particular developmental setting. The more stringent we make our consistency specification, the more informative the notion of consistency is. Okay, the happier we can feel if we have indeed checked that our two sources are consistent. But it's less flexible. Okay, it gives us less scope for changing one without breaking consistency. And sometimes you want to do that because sometimes you're going to say, well, okay, I've got good reason for keeping these things inconsistent right now, and I don't want, you know, some quality control person telling me that I'm wrong. And of course, the more consistency you articulate, the more difficult it is to restore consistency, whether that's informally or automatically. And you probably care about that more if you're doing it automatically, because if you're doing it by human intelligence, you have more scope for just doing the right thing. But programming intelligent behavior is more difficult. But on the other hand, there's potentially more work saved for the user by the automated consistency restoration if you have a very strong consistency definition than if you have a weak one. Okay, my main point here is simply it isn't that there's one right answer. You can't just say we just need to work out what it is for these things to be consistent. That's actually a thing to be decided. Okay. So that hopefully agreed at this point. Let's suppose that we've understood now what notion of consistency we're going to use. So we know what's going to make us comfortable to go on with development, knowing that we're not wrong yet. Okay, the system is the relationship between our models is not broken yet. Okay, and now let's move on to thinking about how we're going to restore consistency. Okay, so in most development, even development that uses models, even development that uses models in rather a disciplined way with specification of what models there are and so on, that restoration of consistency happens mostly via human communication. Okay, it happens mostly through meetings, through people getting together and understanding one another's points of view well enough to say, okay, we've got a problem here, how do we best fix it? And as I think it was Sebastian was suggesting in the chat, that can be a strength, okay, because certainly at the moment, we absolutely need communication and common understanding between humans in order to get things done. And such models, such meetings that surface disagreements via inconsistencies between models and work out how they should be reconciled can be important steps forward in the development process. However, compared with an ideal situation in which, you know, we wouldn't be necessarily talking about expert software developers working with these models, but we might be talking about stakeholders who don't want to be thinking about their lives in terms of software, but just want to be able to get on with their job where they're expert in something else. It's a problem because it requires the humans to understand lots of stuff outside their own model, and it's difficult and it's error prone. And so consequently, it discourages changing the models. Okay, so if you are an expert in one particular concern and you've got a model and you think, actually, wouldn't it be better if I could make this decision slightly differently, if I could change this model in that way, it's a disincentive to you if you've then got to go through a difficult process of having meetings with other people and working out what effects there are on their models and negotiating changes. If you could do it automatically, or even if you could just find out whether you could do it automatically, you might get a lot more flexibility because you might have a much cheaper way of improving the decisions that are incorporated in your model. And a crucial thing to notice here is that the whole point of having different models was that each model excludes some things. Okay, so every model has some information that's not included in all of the other models. You get some very specific exceptions to that sometimes. Sometimes you have models which really do include just the same information and all they are is formatted differently. Okay, and when you're in that situation, and we classically get sort of examples about, you know, different formats for address books and that kind of stuff. That's a situation in which you can expect to take the human element out of it entirely and have fully automated consistency checking and restoration. That's very nice, and we call those bijective bidirectional transformations, but it's not the norm. Okay. So the next thing we have to think about when we're thinking bidirectionally is how much consistency restoration we would like to automate. And there are a number of different valid choices here. And the first thing I want to say is that none is a perfectly valid choice. So you are still thinking bidirectionally if you have articulated what consistency between your models is, and then you decide, actually, in our setting, the right thing to do to restore consistency is to have meetings, is to say, you know, if you run your consistency checker and it says there's an inconsistency between these two models, what I'm going to do is I'm going to pick up the Teams call or the phone or walk down the corridor and discuss with the owner of the other model what we should do to fix it. Okay. So that's that kind of setting. We've got automatic check-in, but we've got all the fixing done by humans. When we're thinking about bidirectional transformations from a formal perspective, we often have the assumption, implicit or explicit, that consistency restoration is fully automatic, that under all circumstances, you can just press a button and have the models restored to consistency somehow. Okay, and that's very nice if you can get it. In practice, the kinds of frameworks that exist or have existed for doing automated consistency restoration are much more likely to be in this state where we say we've got full restoration of consistency, fully automatic restoration of consistency, except that things may go wrong. Okay, and incidentally, if you've used a version control system, you're used to this, right? That sometimes you get conflicts and you just have to manage them. A space which I think needs a lot more exploration than it's had so far, although there has been some interesting work in this area, is partial consistency restoration, where you might want to say something like, we have an automated consistency restoration engine, an automated bidirectional transformation that promises to improve consistency, but it might leave some work for humans. So here you might want to say, well, okay, you know, we're going to do the boring parts where it's obvious that there's only one thing you can do to improve to restore consistency for this particular thing that's gone inconsistent. But there's this other thing where we're going to leave the work for the humans. So, for example, in the case where we're talking about a version of consistency between tests and Java code, where in order to be considered consistent, the tests have to actually pass, then you might say, well, okay, we'll articulate that as our definition of consistency, and then we can perfectly well have an automated consistency checker. Okay, we get that by compiling the things together and then running the tests. Okay, and if they all pass, then we say, hey, yes, good, consistent, and if they don't, we say inconsistent. And then we might say, and we've got a consistency restoration engine that can do some automated restoration of consistency along the lines of, you know, if there's a mismatch between names and perhaps even signatures of tests, it can do it automatically. But if the problem is that a test fails in an interesting way, then we're not going to even attempt to automate that. We're going to say that's for the humans to do. Okay, and that might well be a sweet spot in a particular place. The reference at the bottom is to some work I did a very long time ago about some things we might want out of such things, and since then there's been a lot of work done, for example, by Marshall Chechik's group and others as well. It hasn't really made its way, as far as I'm aware, into mainstream software development at this point. Okay, right. So we've got different levels of bidirectional thinking. So we've got, when we talk about bidirectional thinking, we're talking about thinking explicitly about integration of concerns. And so sort of level 1 is where we are explicitly thinking about consistency. So we might be explicitly saying this is what it means for our concerns to be consistent or not. And then the next level is to say we are programming the checking or the restoration of consistency, and maybe we're going to do that in a general purpose language. Okay, so you're already doing bidirectional thinking at this point. And then the third stage, which in practice is rare these days in current software development, but which one might hope would be less rare in future, is to be programming bidirectionally. So programming in a books language, in a language which is specially adapted to actually programming the specification and restoration of consistency. Now, in practice, I think we're going to need a lot of flexibility, because we are going to have to deal with situations which are heterogeneous in the sense that they involve models which are in different formalisms. Some of them might be text, some of them might be graphical, some of them might be in domain-specific languages, some in general-purpose languages, some in MOF, whatever. And some of the things we want to think about as being transformations already exist. Some of them might come with your development tool. Some of them have been developed a long time ago. Some of them are coming in your framework via your model view controller setup or what have you. There are different languages involved at all levels, and equally importantly, nobody's going to sit down with their multi-million line development and say, "Oh, we're going to redevelop this all in a bidirectional way, and we're going to incorporate automated consistency restoration between all the new models." People are going to want to adopt this gradually, if at all. And so I think what you can imagine is that an organization might start off by saying, well, okay, when we introduce a new model, we are also, as part of that process, going to start off by thinking explicitly about what consistency has to be maintained between our new model and other models that may be around. And maybe at some time in the future, we might start to automate the parts of that seem most boilerplate, that seem like, you know, the lowest hanging fruit for automating the restoration of consistency. And then you might move up from there. Okay, and you might someday, or you might never, reach the point where you've got pure push button consistency restoration. And so I think we have to take quite a pragmatic view about this. Now that, I think, is the point at which I'm going to abandon my slides for a little bit. And I'm first of all going to turn to the chat, and then I've got a lot more stuff that I'm going to say. Antonio's saying, expecting the test to pass is a bit too much to ask. Well, yes, indeed, but we can dream, okay? And you're mentioning the transformation tools context on consistency between BibTeX, XML and DocBook. Yes, okay, that might be a very interesting thing for people to look at. If you are interested in such stuff, I'm just going to visit that. Lots of pictures of the winners, jolly nice. I'm not going to try clicking through those links in real time. Stephen, I'm struggling to understand what automated consistency restoration might look like for a graphical modeling environment that doesn't involve any coding. Modeling for me doesn't involve any code. Okay. So I can give you a graphical example easily enough. So supposing that we are thinking about, and in fact, you've certainly met this if you've done modeling in UML or a similar language where you had more than one kind of graphical model going on. So suppose that you had, for example, a class model, and you also had a sequence diagram. Okay, yeah, so let's think in terms of UML and SysML. So suppose we have a class model and we have a sequence diagram. Okay, now let's try not to get into the weeds about whether that involves having one model or multiple models, but let's think of them as being separate models with a consistency restoration to start with. So you can think about writing down a specification of what it is for the class model to be consistent with the sequence diagram. Okay, so you might want to say, for example, every lifeline in my sequence diagram specifies what instance of what class we're talking about, and all of those classes ought to actually be classes that do indeed occur in my class diagram. And every time there's a message that occurs in the sequence diagram, you might want to say that message corresponds to a method which is actually recorded as existing in the class diagram. And depending on how much information you've got in your particular sequence diagrams, we may also have signature concerns there. And now you can say, so now you can see there that you could automatically check that, you know, and indeed, if you're using a standard UML tool, it probably does. And in fact, it probably, you know, if on a good day, doesn't even allow you to develop a sequence diagram that is inconsistent. And depending on which tool you're using, it may also do some automated consistency restoration for you. But supposing you're using a fairly dumb tool, and suppose that you go along and you say, okay, well, now what I've done is I have changed the name of a class in my class diagram, and that class is one that did actually occur in the sequence diagram. Okay, well, now my two models are inconsistent, and an automated consistency restoration might simply go and change the name of the class where it occurs in the sequence diagram so that it matches the changed name in the class model. Okay, and that's a particularly easy thing to do. Now, a more difficult thing would be supposing that in the class diagram we delete a class of which there's an instance in the sequence diagram. Okay, now it's much less obvious what the automated consistency restoration could do. Okay, so there are design decisions to be made here, and there's nothing easy about it, but thinking about what's going on in terms of consistency specification and consistency restoration is a way of organizing the thought that has to be done. Okay, so there's no such thing as a free lunch. Okay, none of this stuff is going to free anybody up from actually having to make the difficult decisions, but it's a way of organizing thought about what it is that needs to be done. Okay. So next I want to go on and think a bit about what information we need in order to effectively do our consistency restoration. And here we have some quite important decisions that make a difference to what kind of approach you can take. And I have my own biases here, and other people feel very strongly that other choices are correct. So I'll try to explain a little bit about where that disagreement and change and difference of focus comes from. So I hope it's clear, although this is a point which people often get confused about, that we do need, that if we want to restore consistency between a pair of models, let's think about just two models for now, we do need at least access to both models, okay? Because the mere fact that each side contains information which is not present on the other means that it's not possible to completely regenerate one model from the other, usually. Now, sometimes we'll be in the lucky situation where both models contain exactly the same information. In that case, you only need one of them. You can say, I just changed this one, let's just completely regenerate the other one, throw away the old state of the other one, regenerate it. More often, you'll be in a situation, and this is also good when you can get it, where one of your models contains strictly more information than the other. And so particularly in the lens setting and the database view setting, we'll call one of our models the source and the other the view. And in that case, if you change the source, everything is easy. You can just regenerate the view, okay? Because the view only contains a subset of the information in the source. There is only, the way to think about this in consistency terms is to say, given a source, there is only one view which is consistent with it. And it's the view which is the one which is literally just generated from the source, okay? And so provided you've got an up-to-date version of the source, you can generate the view. Okay, and in a situation where you've got a bunch of different models around, if you're able to maintain a single source that has all the information from all your models, so that at any one time you could regenerate any one of the models from your all-seeing, all-powerful, God model, your overall source, that's great. That's a really nice situation to be in. And sometimes you can do that if you're really controlling all the tools that everybody's using, and you don't have to live with kind of legacy. Things are still not totally easy, because if somebody makes a change in a view, you've still got to work out how to update the source. Okay, and that's what lenses are doing. That's the put function of lenses, and there are some interesting questions there. Okay, but more often we're in a situation where we're in a symmetric situation where you've got at least two models and each of them contains information not contained in the other. Okay, and at that situation, in order to do consistency restoration, we do need access to both of the models. But that's not all you might want. So quite often it's very convenient to have more information than that. So one example is that you might want to have some kind of notion of which parts of one model correspond to which parts of the other model. In the interest of time, I'm not going to say any more about that. I want to focus on the next thing, which is to say it's often very good if you know something about what the user did to make the change that caused consistency to be lost, such that you're now trying to restore consistency. You used to be in a consistent state, something changed. Okay, if you know something about what it was that the user changed, the more you know, the better you have the better chance you have in principle of making an intelligent, appropriate change on the other side. So let me give a couple of examples of this. So suppose we are comparing a class model with some documentation for the classes that exist in that class model. Okay. Now, here's one thing that a user might do. Okay, so a user might delete a class. Let's say they delete class A, and then they come along and they insert another class, so class B. Okay, and in that case, we might say that the appropriate thing to do in the documentation in order to restore consistency, which let's say just says there should be some documentation for each class in the class model, and all the classes that occur in the documentation should actually be classes in the class model. So the simplest possible thing there. Then in that case, you probably ought to delete all the documentation that corresponded to the class A, because it's out of date. Class A has been deleted. And then maybe you just insert a sort of default empty documentation template for the new class B. Okay, maybe it says, there exists a class B, and the textual documentation has to be added by somebody. It's not been written yet. Get the technical writer onto this. Okay, but the other thing the user might have done is suppose they come along and they change the name of class A to B. Okay. Now, in that case, the change you want to make in the documentation is probably different, because at that point, you probably don't want all that class A documentation deleted and replaced by a default empty template. It's probably a better idea in that case to just go changing the name A to B wherever it occurs in the documentation that you had. Okay. But if all you have access to at the point when you're trying to automatically restore consistency is the current states of the models, so all you see is that you've got the documentation as it was, with documentation for class A and no documentation for class B, and on the other hand you've got a class model that now contains a class B and doesn't contain a class A, you've got no way of telling the difference between those two situations. You don't know whether the user deleted a class and inserted an unrelated class, or whether the user chose to change the name of a class. Okay. If you can have that information, that enables you to do a better job of automated consistency restoration. Okay, but the trouble is, having it implies that you've got some way of giving access to that information to your consistency restoration process. So you've somehow got a consistency restoration process which is integrated with whatever tool the user is actually using to modify the model. Okay, now if you're controlling the whole ecosystem, you may well be able to have that. But as soon as you are working with, I don't know, a sort of multinational, multi-language company with legacy code and lots of different developers who may even have come from different companies that you bought 10 years ago, and you haven't completely changed all the processes to match, you can easily, with no exaggeration, have hundreds of different tools being used in the various artifacts for a single software system in that company. And there's very likely no way at all that you can actually make sure that all of those tools are going to be consistency restoration aware and are going to provide you with information about what the user changed in order to let you use that information in consistency restoration. So, you know, horses for courses. If you're lucky enough to be in the situation where you can do that, then great. You may well want a consistency restoration approach that enables you to take advantage of that. But the situation in which you say, well, I'm just going to give my consistency restoration process access to the current states of the models is much easier to ensure. Okay, because the chances are your models are saved somewhere. You know, they're probably put in a repository or something. Getting access to that may be much more practical. Okay. So going back to the question of what we're going to write our bidirectional transformations in. So how are we going to? Actually, I think I probably skipped over the slide that says what a bidirectional language is, which is probably a mistake. So let me rectify that, because I'm probably being confusing at the moment. So I did say at some point, I think, that a bidirectional transformation is an artifact that completely or partially automates the process of consistency checking and possibly also the process of consistency restoration. Okay, that's what I mean by a bidirectional transformation. Okay, a bidirectional transformation language is a special purpose language for writing bidirectional transformations in. Okay, so you can write bidirectional transformations in general purpose languages, and I'll say a bit more about how in just a moment. But it's quite nice to have a special purpose language. Why? Because a special purpose language has a chance of recording this stuff much more economically. It has a chance of being specially adapted to, for example, to allowing you to write once, so that you can write a transformation that simultaneously records something about what consistency is supposed to mean and about how it should be restored. And I can show you an example. Now, I wonder what order I want to do this in, actually. Let me go right now to showing you an example in a bidirectional transformation language. I'm going to try to avoid being rude about QVTR, enjoyable though that is. But I am just going to give you an example. Okay, so can you see that? Somebody tell me you can see that now.
It's a bit small. Maybe if you can zoom in a bit.
Yes. I don't need you to be able to see the whole lines, really. It's just a case of seeing something about it. Is that better?
Yep.
Yep. I think in Teams you can zoom as well, if that helps. I always forget how to do it, but there is a way to do it. Yeah. Okay. So QVTR is, or I think these days I can probably just about say was, the object management group's standardized bidirectional transformation language. And what we mean by this is that it's a language with a single artifact which records in one artifact what it is for models to be consistent and how consistency should be restored. And so this is an example from the standard, and it is recording the consistency and how to restore it between a UML model and a relational database model schema. And you can see that it's quite nice and concise, and to a certain extent you can already guess how to read it. I'm not going to go into details. This is not a talk about QVTR, but I just want to demonstrate the existence of special purpose bidirectional languages. So it's organized by relations, and you can think about these as being kind of spiders that you might drop onto each model and say, I want to check that this part of this model corresponds in a sensible way to this part of this other model. And so this top relation package to schema says basically for every package with a given name in the UML diagram, there should be a schema with the same name in the schema diagram, and vice versa. Okay. And the same syntax gives us a mechanism via the semantics of QBTR to say this is what should be true, and this is what the QBTR transformation engine will do if it's not true. And you have not full flexibility, but a fair amount of flexibility in influencing how consistency should be restored. And the limits of that being poorly understood are the essence of what I would say if I were going to say a lot more and be rude about QBTR. Okay, and I'm not going to do that. So let's move on from there and say where I next want to be is slide 26. Okay, so hopefully you can see my slide headed Wire Books language at this point. Okay, so supposing that we are going to say, unfortunately, it's the case. I think it's so. I'll be very interested if any of the experts present would like to disagree with me. But I think, as far as I'm aware at this point, although there has been a lot of very interesting academic and some industrial work on bidirectional transformation languages, I think that today there is no specialist bidirectional transformation language that I personally would want to put on the critical path of an important project in my company. I wouldn't today want to bet the farm on any of the existing languages. Okay, so I think in practice, if you're thinking bidirectionally and you're wanting to automate consistency checking and restoration, you're going to be doing so in a general purpose language. It doesn't matter which one. Let's just say Java. And in order to do that, you're going to have multiple artifacts because, you know, that's how general purpose languages work. But what you can do is you can write. I've said programs here, but you might, for small things, just be thinking about functions. And actually, you may well have done this, even if you haven't really quite thought about it in these terms, if you're writing user interfaces, for example. So you may well have one program or one function that checks consistency. So if you've got two types, you might say my consistency checker is going to take an argument of each type, and it's going to return true or false to say, are these arguments currently consistent or not? So you might say, I'm going to take in a representation of my my class diagram and a representation of my sequence diagram, and I'm going to say, yes, that's fine, or no, that's not fine. Okay. Or I might take in my Java program, because this is what a test runner does, right? It takes in a Java program and it takes in a test file, and it runs the tests on the test file, and it gives you a green bar or a red bar to say, you know, do the test pass or not? Okay. So in many special cases, we already know how to do this, but you can also think about programming it. You know how to do that. And separately, you can have programs that restore consistency in either direction. Now, on this slide, I have implicitly made some. I've planted my flag in a particular point in the design space of how we're going to do bidirectional consistency restoration. So my assumption here is that consistency restoration takes one argument of each of our model types and returns us a new version of one of them. So it's like saying, if I'm taking a class diagram and a sequence diagram, then the consistency restorer might return me a new version of the class diagram. And the idea is that it's going to return me a new version of the class diagram, which is like the old version of the class diagram, like the one that was an argument to the function, except that it has been changed so as to be consistent with the sequence diagram that was the other argument to the consistency restorer. Okay. And because this is bidirectional, we probably expect also to have a different function or program that has the type m cross n to n, which will allow us to restore consistency in the opposite direction. Okay, it'll still take us a class diagram and a sequence diagram, but instead of returning a new class diagram, it will restore a new sequence diagram. Okay, and if you've got a class diagram and a sequence diagram, let's say, which are currently inconsistent, and you want to restore the consistency, then which one you want to change will depend on the scenario. Okay, you know, has one of them just been reviewed? Do we know one of them's more reliable than the other? You know, is the person in charge of one of them more important than the other? You know, what do we have to do in order to make sure that we just don't go around in cycles? And I've completely elided here something that I just briefly alluded to early on, which is to say, although this is a very useful simplifying assumption, sometimes it's not what you want. Sometimes you actually really would want both of those things to change a little bit. You'd want some kind of negotiation to go on to restore consistency. Okay. Those tasks are indeed tightly coupled. So, for example, if you're talking about quite complicated model types, then you're going to find that all three of those programs, the consistency checker and the two consistency restorers, are going to have code which sort of walks through the structure of the models. And then if the structure of the models changes, you're going to have to go through and carefully modify all three programs, and you're going to have to make sure that you've done that in a way which is correct in all three directions. So there's a certain amount of pain to be endured if you want to have a bidirectional transformation which is written in a general purpose language, but it is possible to do it. Okay, so the fact that we would like to avoid that pain is the reason for saying in an ideal world we would have books programs, we'd have special purpose bidirectional languages, but right now we don't. And so the fact that this is painful is also perhaps a reason why you might perhaps want to automate less than in an ideal world you might ideally want to, because you might want to spare yourself the pain of having to maintain a very complicated ecosystem of bidirectional transformations. So it is kind of courses to courses. We're in a state at the moment where a considerable amount of intelligence is required in order to work out what the best thing to do in your particular setting is. But I think, and I claim, that actually once you start thinking about bidirectional transformations as a way of organizing your thought about consistency in the world, you will find that it's a good way of keeping your head straight and not running yourself into unpleasant situations. Now, probably given the time that this is going to be the last chunk of material that I get to, because the last thing I want to talk about a bit is a thing that's going to be essential to think about if you are writing your own bidirectional transformation code in a general purpose language, and is also if you are conversely trying to design the world-beating specialist bidirectional language, which is to say, what collections of consistency checking and restoration behavior do we want to allow? What do we want to consider legitimate? Okay, so let me illustrate why that's even a question by saying, to start off with, here's an example of something that would not be legitimate. Okay, so supposing I have a consistency checking program which does something very careful and checks whether your programs are consistent or not and gives you a true or false answer that you're happy with. And your consistency restoration function takes two programs, and if they are inconsistent, it deletes them both. I'm told that there was a version of the Glasgow Haskell compiler that did this once. If your program contained a type error, it deleted it from the disk. I'm told that it's not actually a fully released version of the compiler, but I sometimes think, wouldn't it be interesting if you provided your students with such a compiler? It would certainly, actually, that would be a really terrible idea, right? Because it would cause them to not compile until they were almost certain that things got to be. But yes, exactly. Both sides are perfectly consistent now. So that would be, and in many ways, this is one of the reasons, actually, incidentally, this is one of the reasons why, when you're thinking about things formally, you have to be very careful if you start dealing with formalisms where you're going to allow both models to be changed in order to restore consistency. Okay, because when you start saying the property we want of our consistency restorer is that it does indeed restore consistency between the programs, you have to take quite a lot of care to make sure that you limit how much information it's allowed to delete, because otherwise the consistency restorer that just deletes both models is going to have lots of good properties. Okay, so yes, I mean, and it's closely related, right, to the observation that every program can be every program contains a bug, and every program can have its length reduced by at least one line. It follows that every program can be turned into a program that's only one line long, and the one line will contain a bug. There was one word in books for basically asking for a minimal set of actions to restore consistency, but I always forget it. I normally just say least change. I'm going to come to that in a moment. Yeah, okay, let's start at the beginning with the most obvious things, okay? So these are the things that we just want to keep us sensible, okay? We probably do want our bidirectional transformation to be what I call correct, okay? And what I mean by correct is after you have restored consistency, the result is consistent. Okay, profound, yeah. So in terms of our m cross n to m function, what that says is the m that it returns is consistent according to the consistency checker with the n that was the argument. Okay. Now the next thing you want is the thing that I coined, and I'm never sure, and I've made myself unpopular in some quarters for this, and I'm never sure whether I regret it or not, but I've called it Hippocratic, okay, which is to say, if you take two models which according to your consistency checker are already consistent, then your consistency restorer, if you run it on the same two models, should do absolutely nothing. Okay, in other words, it should return you something which is exactly the argument that you gave it. Now, this, somewhat to my surprise, is already quite controversial, because what some people would like to say is, well, but because what I'm actually going to do is I'm going to take my two models and I'm going to turn them into a kind of super duper organized multi-model, and then I'm going to reproject out. It's going to be a consequence that the thing I get back may be in some sense normalized. It may, for example, have been, re-indented or, re-laid out or something, and that should count. And so they want to have some kind of equivalence relation where they really want just to say the thing that's returned should just be equivalent to the thing that was given. But Hippocratic, we insist these things are exactly right. Now, after that, things get a lot more interesting and a lot hairier, because it turns out that it's very easy to write down properties that you would like all bidirectional transformations to have. And this is fine, except that you then find out you can't have them. So the classic example is the thing which is called history ignorance, or sometimes it's called strong undoability. And what this amounts to is saying, if you make a series of changes to one model, and from time to time you restore consistency with another model, so you have one model you're working on, and there's another model, and from time to time you press the button and say, okay, I've reached a good staging point, now please update the other model to be consistent with the one I'm working on, then history ignorance says it doesn't matter when and how often you press that button. If you go through the same process with the model you're changing, the result on the other model will be the same. Okay. And that's a very nice property to have. And you can see that if you were trying to incorporate bidirectional transformations directly in your tool chain, you would really want it, okay? Because you would want the work of the people on the model that's not being changed to be affected in exactly the same way, regardless of when you're, I don't know, maybe it's running periodically, when your consistency restoration process runs, whether it's running periodically or whether it's running when the person on the other side presses a button or whatever it is. Unfortunately, you practically speaking can't have it. And the way to see that you can't have it is to think about something like this. Suppose that the model that's being changed incorporates something that on which the other model depends, but such that the other model also has some other information kind of hanging off it that's not reflected in the model that's doing the changing. Okay, so let's go back to our class model and sequence diagram example again. Suppose we're changing a class model and there's a sequence diagram which starts off consistent with it. Okay, now suppose that our editor of the class model, let's just say for simplicity, suppose they delete all the classes. it makes not much difference if we delete one class, but let's just say they delete everything. Maybe they even do it by accident. Okay. And now, whether automatically or by button press, consistency gets restored. Now, at this point, pretty much what has to happen is that the whole of the sequence diagram has to get deleted. Okay, you can't have a non-trivial sequence diagram that's consistent with an empty class diagram. Okay, and now we say the person editing the class model says, "Oops, I didn't mean to do that. I'm going to put all these classes back." Okay, and they restore the model back to exactly what they had it at before. And now they say, now I'm going to press the restore consistency button, or the thing's automatically going to run so that the sequence diagram gets restored. Okay, there's no way that sequence diagram can get put back to exactly what it was, because the information about what's in the sequence diagram is simply not there in the class diagram. Okay, and so the two situations which are actually no consistency restoration went on at all, because the consistency restoration engine happened to be down for the whole of this process, and so it was completely invisible that this deletion and then reinstation had happened. If that's the case, then we're in luck. The sequence diagram is exactly the same as it was to start with. Okay, but if the consistency restoration happened while there was nothing in the class diagram, then the sequence diagram is gone and nothing can get it back. Okay, and that example is why that bidirectional transformation between those two things cannot do what we would like it to do and be history ignorant. So history ignorant is a property that the category theorists tend to insist on, and they get away with it because they assume that they have more information than just the state. They assume that they have intentional information about what changed, but which in practice we cannot have. So that's one example. And another example, a whole category of problems which I could talk about for another hour and a half, but I won't because we've only got 3 minutes left, is indeed least change. So Hippocraticness says if no change at all is required, then the bidirectional transformation should do no change at all. And if you're implementing your bidirectional transformations in a general purpose language or otherwise, actually that's quite easy to ensure. You can ensure that by just saying the very first thing my consistency restoration function will do is run the consistency checker. And if the consistency checker says consistent, I'm going to return and I'll do absolutely nothing else. That's an easy, cheap way to make sure that you get Hippocraticness. But what you really want is not just that. What you want is if there's a tiny change, then you really want a tiny change to result. And what is not quite the same, and the fact that this is not quite the same is in itself where part of the interest comes from, is what you really want to say is the consistency restorer should not change any more than it really must change in order to restore consistency. That's least change. And there's, I can point you to a paper that talks in a lot more detail about what that means, and why it's not an easy question to say what that really should mean afterwards for anybody who is interested. But I've now talked for about 88 minutes, and so it's time for me to stop talking and say, are there any quick questions at the end before we run out of our slot?
Maybe one question,
Mm-hmm.
Rita. Any thoughts on what facilities a modeling tool or a model management framework needs to provide in order to enable a kind of efficient bidirectional transformation?
Oh, lots, yes. Gosh, are there any I can put in 30 seconds?
So I'm thinking, things like immutable model element IDs, for instance.
Yes. I mean, it's intimately bound up with what information you want to make available to your consistency restorer. So if you want something like QBT's trace links to be available, then yes, you're going to need immutable model elements, and I'm sure that's the kind of thing you're thinking about. If not. In practical terms, you might well want that kind of thing as an efficiency aid, even if you wanted strictly to insist that it couldn't make a semantic difference. You probably know that I did some work a couple of years ago about the relationship between networks of bidirectional transformations and build systems, and thinking about the idea of having a framework for multiple models in which there would be a separate component or builder whose responsibility would be to manage the process of consistency restoration between any model and its neighbours, so between any model and the things that have non-trivial consistency restoration, non-trivial consistency relations with it, and it would be really nice to have some ideas like that incorporated in a model management framework, and sort of, you know, one could imagine going all the way through and actually having something that really enables, you know, the sort of push button rolling through of changes that I wrote about. And if you're interested in talking about that, we should absolutely talk about it.
Yeah.
Couple of things in the chat. Let's see. Inconsistency checking restoration. How can we deal with bad models such as incomplete or informal models? Oh, that's an excellent question. Yes, because everything I've been talking about currently has been assuming that we can take a model in whatever state it is as read. Yeah, this is not something we normally think about very much. You can certainly imagine having a sort of gateway to your consistency checking and restoration process, where you basically have a pre-check where you say, you know, first of all, check each model independently and say, is this model good enough to be legitimate input to the bidirectional transformation process, and just refuse to go any further if not. But yeah, that's not something that's had as much attention as perhaps it might. There's an argument that says, well, you should just handle it. You should say, you know, perhaps, you know, if you're allowed to record a model at all, then it's a model and you should just handle it. But I think perhaps the gateway, the sort of gateway check model might actually be more practical.